Swayam Prabha. Digital India. Educated India.
So, suppose strictly less than G star, then by Max-Flow-Minkert theorem, min cut size is also equal to f less than G star. Not just that, the max flow algorithm will actually give you a min cut as well. That is the beauty, right. Not only there is the min cut is f, when the max flow stops, the proof of correctness of why we have a max flow is because from the flow I can actually get a cut whose capacity is equal to f. So, max flow algorithm will give me that. So, let us look at the min cut, right. So, I am going to write and the max flow algorithm will so, let us recall our graph again. So, these are the xy pairs and this is my vertex set minus 1 and this is my t. So, what is a cut? So, ST min cut, right? What does it mean by ST cut? In a directed graph like this, what is the definition of an ST cut? Exactly. It is simply a partition of the vertex set, right. It is a partition of the entire vertex set such that one contains S, other contains T and the capacity of the min cut, right. So, when I say cardinality, it is the capacity. It is exactly look at all edges from with one endpoint in S, one endpoint in T, look at all edges from S to T, add their capacities and that is the capacity of the min cut, and max flow min cut theorem says that that capacity is actually equal to max flow. Okay. So, I do not know how the cut will look like, but as she said one partition contains S. So, let us say this is one part of my cut and this is another part of my cut, right. So, partition is, so A and B is the partition of the vertex set, sorry, this one contains T as well. And I want to now look at the capacity of the cut. What is the capacity? Where edge is going from this side to that side and look at the capacity, right. So, let me have another better picture of the possible cut. So, I have S here, so one partition contains whole partition of the vertex set, the other partition contains this. And the capacity of the edges are, maybe let's see if we can get, these are the kind of edges. These are the edges I need to measure and look at their capacities, right. Okay, so let us make one observation first of all. Suppose okay, one claim I want to make, which will finally will help us complete the proof, is that look at, so the set here are xy pairs and this is V minus 1. So, xy is in A if and only if x in A and y in A. Okay, what do I mean by this, right? So, this A part will contain some pairs and some vertices like this, right. Similarly, B part will contain some pairs and some vertices like this. Okay, that is because it is a partition of the vertex set, and my vertex set contains these pairs for which games are left and my vertex set in this graph plus S and T. So, the first part will contain some pairs and some vertices like this, and this part will contain some pairs and some vertices here. So, what I am saying is if you have an XY pair here, then so X and Y are necessarily in the same set A. Let us try and prove this. Okay. The claim here clear. Suppose there is team 5 6. If 5 6 pair is sitting here in my cut, then the nodes 5 and 6 must also be in A, cannot be in B, is what I want to say. Okay. So, it is an if and only if statement, we need to show both things. So, let us try one direction. The pair X Y is in A implies X in A and Y in A. Suppose not, suppose X was here. Recall what is the capacity of this edge? Infinity, remember this is the reason we put infinity. So, it cannot be a min cut. I know you can't have a min cut with, because we said the capacity of the min cut is, what is the assumption? The capacity of the min cut is some number which is strictly less than G star. It is a finite number. So, this edge cannot be in the cut. So, X must be inside, Y must be inside. So, this is easy. This direction is easy, right, as the capacities of X Y to X edge and X Y to Y edges but the capacity of the cut we are looking at is finite. The converse direction. So, conversely, suppose X is in A and Y is in A, but X Y is in B. Okay, what, let us look at a picture of it, right. So, in my A there is X and Y, but X Y is in B, and you have S here and we have T here. Let us look at, yeah. So, what are the edges in the cut here among these vertices? Recall our directed graph, how they look like, right, what are the edges. So, in the directed graph, what is an edge from A to B among these vertices? So, there is nothing about S T, S is connected to X Y, remember, with the capacity of G X Y. X and Y are not connected this way, but X and Y are connected by, yeah, X is connected to T and Y is connected to T with some capacities. These are the edges which remain like this. Suppose I pull X Y back, what happens? And then say S here, X, Y, and suppose I put X, Y here and T here. Now, what happens to the cut? Well, the X to T and Y to T cut will remain, but the S X Y weight has come down, it is no longer there. But since this number is positive, remember G X Y is strictly positive, I would have reduced the cut size capacity, right. So, if X Y is here, but X Y is sitting here, if you just move X Y there, you actually get a cut with lower capacity. Since we assume that this is a min capacity cut, it cannot happen that X Y is sitting here. So, I have proved the converse, right. So, if X and Y are in A, then X Y is in B is contradiction. So, I can say okay. So, what have we, okay. So, now let us just go back and look at the cut and see how the cut edges are. So, my S is here, this is my pairs, this is my vertex set minus 1, this is T, and I have directed edges going like this. When I have a cut, let me use a different. So, I have a cut which is one contains A. So, this is my A, and another set which contains, and this is the min capacity cut, and we have shown that x y is in A if and only if x and y are in A. Good. So, now let us look at the capacity of the cut. But before that, let us go back to our goal. What is our goal? You should not get lost about our goal. So, yeah, so I have found out that flow value is less than G star, right. I have ran my max flow. If it is equal to G star, that the flow algorithm gives you a way of outcome of the game, so that my team survives. But now I have run and it turns out the flow is less than G star. I want to argue that my team won't survive. How am I planning to argue? I am going to exhibit you a subset of teams where that averaging thing happens, right. So, what is our goal? To get a subset of teams, right, which satisfy some calculation numbers, right. I have to give you some subset of teams. So, what is a natural candidate for a subset of teams from the min capacity cut, right? The teams are all here, some are in A, some are in B, okay. So, this is my teams, right. This is the vertex set which is all the team, these are pairs of games left. So, my teams are all here, some are in A and some are in B. Let us say arbitrarily I am going to choose the teams in A, and I hope that they will be my witness team, okay. So, let T equal to A intersection my vertex set, right, this vertex set. So, this is my A T, and I am hoping that this will give me the witness set. But let us now compute the capacity of the cut, okay. So, what are all the edges crossing the cut, okay. Let us see. So, S remember is going, so in the cut what are the edges from S? From S these are the edges, right, these are the edges that there are no edges from S to here anyway, there are edges from here, but these guys are in A itself. So, if I want to say about cut means that edges with one endpoint in A, another endpoint in B. So, I am going to look at my entire set A and look at all edges coming from A to B and measure them, count them, something, look at their capacities, right. So, these are all the edges coming from S to these vertices, these are games pairs, right. So, this is, so what did we assume as the cut capacity is F, right, capacity of the cut is equal to F, and we know that it is less than G star, and this is equal to summation G x y, because these edges have capacity x y, right, where what can you say about these x y pairs? Well, there none of them are in T, right, anything in A their corresponding x y's are here. So, x n is not in T and y is not in T, it is that pairs, because so this is all pairs for which the games are left. But what we argued is that if you have a pair which is sitting in A, then the corresponding x and y must also be sitting in A, right. So, this is if and only if. So, if for any T the corresponding x y's are sitting in A, so these pairs are guys for which x is not in T and y is not in T, and for which the capacity is Gxy. Okay, what are the other edges from capital T to very small t, right? That is the set of capacity edges left. So, what is their capacities? For each such vertex, if you pick any vertex here, remember what the capacity we assigned in my graph? M minus Wt, right? So, it is M minus Wt T in T. This is it. So, this is equal to, I am going to say G star minus this quantity. Okay, this is either x is not in T or y is not in T, right? That is what it means, that because if both are in T, then x y must be in T. So, the guy is outside means that at least one of them is not in T. So, this is G star minus summation. So, this quantity is G star minus summation G x y, both are in T, plus m times cardinality of T, this is the first term, minus summation W T T in T. So, the capacity of the cut, which is equal to F and we know is less than G star, is this quantity. Okay, maybe you can tell me what it is. So, it is G star minus m times T plus, yes, summation G star, so plus m times T minus J x y minus W T. Okay. Yes, okay, assuming the calculations are all right. Everybody with me? No, I am come to G star. So, this is the capacity of the cut, okay, these two. I have written, so this quantity is exactly here, m times cardinality of T minus summation W T. This is exactly copied here. This quantity I have written it as G star minus summation G x y x y and T, because G star is all the G's together. So, I have subtracted out those, both are in T. Okay. Did we get what we wanted? If you just do some calculations here, G star cancels here. So, what did I get? Summation G x y x y in T plus summation W T T in capital T is greater than m, right? Magic. So, let us summarize what we have seen, right. So, just to summarize, we had some wins for every team so far and there are some matches left. We wanted to know, is there some outcome of these leftover games so that my favorite team survives. First, we saw some averaging argument, so that if that average of the remaining teams wins plus whatever is left, if that is more than what is the maximum I can get, then no chance. But we saw that that is not the only condition, because there are examples where even the average is not more, but still my team cannot survive. What did we extract out of it? Well, there is some subset of teams for which this happens, then my team cannot survive, right. Now, the question is it if and only if? Suppose there is no subset for which this happens, can I conclude that my team survives? And that is what we proved. How did we prove this? We set up a network flow network with capacities, and we said run max flow algorithm on this. If the max flow value is equal to the total number of matches left, then this max flow solution gives me a way of outcomes, right. Yeah, this is what it is. Because once you run this max flow, it tells you how each of the games can result such that nobody gets more than m. This is good, but what I want to know is the converse. Suppose max flow is less than that, then is it true that my team does not survive? And how do we prove it? If you can give me a subset of teams for which this averaging team thing works, then I will be happy about it. And we said yes. So, what we do is, suppose max flow is less, then we know the max flow value is min cut, and we proved a little claim about the pairs, and then we looked at the capacity of the cut. Okay, so, we proved this, that if a pair is in my first part of the cut, then the individual teams are also in the same part of the cut. From there, now we said, okay, having proved that, let us look at the capacity of the cut. We went through, carefully counted what are the edges crossing the cut, looked at their capacities, and we added them all, and from there we got a subset of teams. That subset is exactly that subset of teams that intersect my A part of the min cut, and that has this quantity exactly the total number of games left between them plus whatever they have won so far divided by the number of teams is strictly more than m, and m is the maximum my team can get. So, one of them in this is going to get more than m. So, my team does not survive. So, right, if and only if things are very nice, because it gives you a complete characterization. If this happens, here is a sequence of outcomes. If it does not happen, I will show you a witness. In fact, the witness subset is also found in polynomial time, right. We do not have to run through all possible subsets, because the max flow min cut theorem gives you the final thing which gives you the cut. How do we get the min cut? Can somebody tell me how we got the min cut from the max flow Ford Fulkerson algorithm? When does the max flow algorithm stop? There is no ST path, right. So, in the residual graph there is no ST path. Good. Now, so it's sort of like a greedy algorithm. If you think about max flow algorithm, it starts with the some zero flow, and then see can I send some more flow through some edges, and we will keep sending it. The only little clever thing, important thing is that we also add the backward edges of the flow which has been there, so that we can take back our decision, right. So, if I decide to push some 50 through an edge, the residual network gives you an option to take back something, right. That is what it is, right. So, if I push 50 through this, then my residual network will have this edge with this capacity, right. So, I can find an path and so on. So, other than that, is essentially some sort of a greedy algorithm. We will keep pushing until the residual network has no ST path. Okay. And why is that enough? How can we prove that when we reach that stage, you cannot push anymore? You cannot push anymore in our algorithm in the way we have been proceeding, because we have always been looking at the augmenting path in the residual network and pushing. But why is that the correct way to do all the time, right? And so, this requires a proof of correctness, and that is proved. So, how do we get the min cut again? Anybody remembers now? Exactly, and that is my capital S, right. So, I have S and all vertices reachable from S in the residual network. This is my A, and B is the remaining vertices. Why is S here? Because S is reachable from itself, right. Why is T here? because there is no ST path, that is why we stopped, right. The final residual network, there is no ST path, so T is not reachable from S, we stopped. And we claim that this is a partition. What is a cut? Cut is a partition of the vertex set. I have given you a partition of the vertex set, and the claim is that this cut capacity is equal to the flow whatever you have got so far. Why? Well, if you look at any edge here in the graph which goes from here to here, what can you say about their flow? Current flow on, so there is some flow, right, you have some flow. So, the graph told you some flow here, you stopped because the residual network has no ST path. Now, you look at any edge where one endpoint is here and one endpoint is here, what can you say about the flow? The residual graph, this edge does not exist. Why does it not exist? Because if this edge existed, y would have pulled y here. Why is y here, right? Y is here because there is no S to Y path. X is here because there is an S to X path. If this edge was there in the residual network, y would have been here. So, this edge is not in the residual network. Why is it not there? Because its capacity, its flow is equal to capacity, right? Flow is equal to capacity here. So, this is true for every edge like this. So, the capacity, now for any backward edge again the flow is 0, because otherwise the forward edge would have been in the residual network. So, the total capacity, the flow here between A and B is exactly the flow, original flow, and which is equal to the capacity, sum of the capacities of all the edges in the cut. So, here is a cut where the flow and capacity are the same, right. So, how do we get the min cut? No problem, you just construct the residual network and do a reachability, do your BFS or DFS starting from S, all vertices reachable from S is one part, the remaining is the other part, and that is your cut. Okay. So, you get cut for free. As you finish your max flow, you also get your min cut. The fact that it is a min cut requires some argument, and hopefully that has been done, right, because every cut is sort of a bound on the flow you can get. So, once you reach a point where the flow is equal to capacity of some cut, then that cut is the minimum and the flow you have is the maximum. Okay. So, now let us just go back to the algorithm. We saw that if the max flow is less than G star, then when we run the max flow, we also get this min cut whose capacity is less than G star, and in that cut I look at all the teams vertices in my set A, they satisfy my averaging condition, tells you that one of them is going to get some more than the maximum my team can get. The point of this is, once you look at the problem, it has nothing to do with graph, it has nothing to do with flow, it is nothing, but somehow it tells you the power of network flows. A lot of different kinds of problems. If you look at Kleinberger and Tada's book, they give you a lot of applications of network flows for various different, airline scheduling, all kinds of different kinds of problems which you can model using network flows.